Bam! Mr. Tarrou, we just got done learning how to evaluate or estimate a definite integral using the trapezoidal rule and Simpson's rule. Well, if you're estimating definite integrals, then the next logical step is to analyze, what kind of errors can we expect from those estimation techniques. So what is the maximum error to expect from the trapezoidal rule and Simpson's rule? Or in other words, what is the difference E, which we're going to be seeing in our formulas, between the definite integral from a to b of f of x dx and the approximation from that trapezoidal or Simpson's rule again, which we're working through because it's not that difficult to come up with an integrand that is not, that you can't take the integral of easily with the elementary techniques that we've learned so far. So if f has a continuous second derivative on a closed interval from a to b, then the error E in approximating that definite integral from a to b of f of x dx by the trapezoidal rule is the maximum, or excuse me, the absolute value of the error is less than or equal to b minus a cubed over 12n squared times the maximum value that you get from the second derivative on that closed interval. Okay, so again, it's times the maximum of the absolute value of the second derivative on that closed interval where x is greater than or equal to a and less than or equal to b. So we're going to do a lot of practicing of finding derivatives again. We're also going to be reviewing how do you find an absolute max or min on a closed interval. Now for the Simpson's rule, if f has a continuous fourth derivative, so again, multiple steps of finding those derivatives on a closed interval from a to b, then the error E in approximating the definite integral by Simpson rule is the absolute value v again, because we can over or underestimate the values that we get from our estimation, can over or underestimate the actual definite integral, is less than or equal to b minus a to the fifth power over 180 times n to the fourth times again the maximum of the fourth derivative on that closed interval from a to b. So you're going to see me as we do these examples. We have done a lot of derivative problems up until this point, and we have talked about finding absolute max on a closed interval. So as I go through these four examples that we're going to have in our lesson, there's going to be a lot of me reviewing, not reviewing, but revealing the solutions one step at a time after I introduce the problem, and then I'll go over my work at the end. So it's a good opportunity, it'll be a good opportunity for you to pause the video, practice those skills on your own, and see what answers you get, and then check them with what I have. So first example coming right up. So for our first example, we are going to estimate the errors in approximating a definite integral with n equals 4 using the trapezoidal rule and the Simpson's rule. We're not going to be estimating this definite integral, which, by the way, we could do this particular problem with the first fundamental theorem of calculus. But if we were to estimate that definite integral with trapezoidal or Simpson's, what would be the maximum possible or expected error from those approximations? Now, having the rules back up here again to remind you one more time, we are going to be looking for the maximum of a second derivative on a closed interval for the trapezoidal rule and the maximum of a fourth derivative on that closed interval for Simpson's rule. Well, remember earlier when we were finding maximum, absolute max or mins on a closed interval, if I just gave you a function, we found the first derivative of that function and then set it equal to 0 and looked for solutions, and we also looked for what values of x or y in that particular case you're doing that would make the first derivative undefined. In other words, we looked for those critical values. And then we went back to the original function and tested that function for the endpoints in the closed interval and the function's value at all of the critical values that we found looking at those first derivatives. Now in this case, if we're looking at a maximum of a second derivative, I'll be analyzing or looking for critical values using the third derivative on that closed interval, and using the fifth derivative, looking for critical values for the fourth derivative on that closed interval from a to b. So I'm going to step off and work out, all of those derivatives that we're going to use for the rest of this example. So we have our 5 derivatives laid out. Now we're going to be looking again for the trapezoidal rule, the maximum of the absolute value of f double prime of x. which means that that I'm going to be taking a look at the third derivative and looking for critical values that are on that closed interval from 1 to 3. So our third derivative is negative 24 over x plus 2 raised to the fifth power. And where is that going to be equal to 0? Well, the only way a rational function is equal to 0 if the numerator is undefined. So this has no solution. And again, we're looking for critical values here. So while that has no solution, we can look for where the third derivative is undefined. And that is going to be at x equals negative 2. So the third derivative is undefined at x equals negative 2. Well, that is not on our closed interval from 1 to 3. So that is really not going to be a critical value for consideration in this particular problem. All we have to do to find the maximum value, the absolute value of the maximum of the absolute value of f double prime of x is plug in the values of 1 and 3 and see which one comes out to be bigger. So f double prime of 1, well, that is going to be, where's f1? Here we go. So we have 6 over 1 plus 2 raised to the fourth power. That is going to be 6 over, now that, 3 to the fourth power. So 3, 9, 27, and 81. And we are looking for, sometimes I forget this, we are looking for the absolute value of the second derivative, the maximum of the absolute value. So that now is still going to be 6 over 81. Now, looking for testing that other endpoint of 3, we have the absolute value of f prime, double prime, of 3. That is going to be 6 over 3 plus 2 to the fourth power, which is going to be the absolute value, and I'm forgetting all those absolute values everywhere, of 6 over, now 5 to the fourth power. Well, 5 times 5 is 25, times 5 is 125, times 5 again is 625. If I could write. There we go. And we can see that our maximum value is occurring for the second derivative is occurring at the end point or the end of the closed interval of 1. So the maximum error that we can expect for the trapezoidal rule is going to be less than or equal to b minus a. So it's going to be the upper limit minus the lower limit, 3 minus 1, raised to the third power over 12 times n, the number of subintervals that you're using. I believe we define that to be 4, raised to the second power, times the maximum that we got, the absolute value of the maximum of the second derivative, which was 6 over 81. Don't forget that absolute value part of the equation, by the way. And that, right off the top of my head, I'm not going to do, that right off the top of my head, do I have the right sheet of paper, is going to be, oh, I see here in my notes, I didn't reduce that. 6 over 81 reduces down to be 2 over 27. I should have seen that they were both divisible by 3. So that reduced, and this whole thing comes out to be a error, the absolute value of our error is going to be less than or equal to 0.003086. Now we're going to do the same thing with the Simpson's rule. It's really the same process, except I'm going to be using the fifth derivative to look for any critical values on our closed interval, and then finding the absolute value of the maximum value that the fourth derivative takes on in that closed interval. So I'm going to just reveal that one step at a time. So just one more time, looking for the maximum of the absolute value of the fourth derivative, we went to the fifth derivative and looked just to make sure there wasn't any critical values on that closed interval from 1 to 3. Very similar equation, so again we found that the fifth derivative was undefined at x equals -2, so there was no critical values on that closed interval. So you see me, I'm just testing the fourth derivative at the lower and upper end of that closed interval, finding the greatest value, finding the maximum of the absolute value of that fourth derivative, and just, plugging it into the Simpsons rule. You'll notice that the Simpsons rule is giving us a smaller sort of possible maximum error than the trapezoidal rule is. That's very common, of course, if you're trying to track the movement of a curving, constantly moving function with, say, a parabola as opposed to a bunch of straight lines. You will tend to get a smaller error. Now, you can see this all looked very, very similar between the two. In the next example, though, before you cut the video off, we are going to be looking for a value of n, a required number of subintervals to meet a requirement of a maximum error, as opposed to these examples where we had a fixed number of subintervals and we were looking for the error from that. So kind of just working the problems a little bit in reverse. Bam! Alrighty then. For our last example, worked two different ways. We're going to find n such that the error in the approximation of the definite integral is less than or equal to 0.0001 on this definite integral from 0 to 1 of sine of pi x dx. So how many subintervals, again, would I need on this closed interval from 0 to 1 so that the maximum possible error from that approximation is not going to exceed that condition of 0.0001. We're working the problem sort of backwards, finding n as opposed to being given a fixed n. And there is our n in our formulas right there in the denominator. And what you still see in here, though, we're using these rules. So we're still going to have to find the maximum of the absolute value of the second derivative and the maximum of the absolute value of the fourth derivative. I think I finally got that down, saying that in this lesson, on the closed interval. So I'm going to step off again, find those 5 derivatives, all the way up to the fifth derivative of the sine of pi x dx, and continue with the problem from there. So here are our 5 derivatives based on the original function f of x is equal to the sine of pi x dx. We're going to be working on finding the number of required subintervals for the trapezoidal rule, or n for the trapezoidal rule, which means we want to find the absolute value of the second derivative, the maximum of the absolute value of the second derivative. So that means I'm going to look to the third derivative for critical values on that closed interval from 0 to 1. And again, we're doing the trapezoidal rule here. So taking the third derivative, we've got negative pi cubed times the cosine of pi x dx. And where is that equal to 0? Now, by the way, this function, the cosine function, is a continuous function along the x-axis. Of course, we know that, and it is never going to be undefined. So we're just not going to include the dx notation of this equation. And again, set that third derivative equal to 0, looking for critical values for the second derivative. We're going to divide both sides by negative pi cubed, which of course is going to leave us with the cosine of pi x is equal to 0. And we want to get that cosine function away from 0. So we're going to take the inverse cosine of both sides and get pi x is equal to the inverse cosine of 0. Hopefully, if you know your unit circle very, very well, you're just saying the answer automatically. The inverse cosine of 0, where on the unit circle is the cosine value equal to 0? There's 2 places, but I'm going to work on the first, or the smallest angle measure. That's going to be pi over 2. Now, trying to solve for x, we're going to divide both sides by pi, and of course get that x is equal to 1/2. So now this time, unlike the previous example, we do have a critical value that we need to test on the closed interval because 1/2 is between 0 and 1. So we're going to, again, needing to find the maximum value of the absolute value, don't forget the absolute values, of the second derivative. On that closed interval, we need to find what is the absolute value of f double prime of 0, the absolute value of f double prime of 1/2 and the absolute value of f double prime back at 1 again. Well, plugging 0 into this second derivative gives us the absolute value of negative pi squared times the sine of pi. Now x is going to be 0. Don't include the dx again, of course. And that is going to come out to, now the 0 times pi is 0. The sine of 0 radians is equal to 0 because it's the y-coordinate on the unit circle, of course. And so this whole thing is going to come out to be the absolute value of 0, which is 0. Now plugging in the 1/2 value, we have the absolute value of negative pi squared times the sine of 1/2 pi, or pi over 2. And again, don't forget the absolute value symbol. This is the problem why. The sine of pi, well, not the only one, but the sine of pi over 2 is equal to 1. So we have 1 times negative pi squared. So we have the absolute value of negative pi squared. And of course, now, because we're looking for the absolute value, that's going to cancel out the negative sign. And our final answer is pi squared. Going through the value of 1, that is going to be the absolute value of negative pi squared times the sine of pi times 1, or just pi. And the sine of pi is, of course, going to be 0 again. So we are looking at the maximum value of the absolute value of the second derivative on the closed interval is going to be pi over 2. So just for time purposes and making sure that all comes out neat, let me step off and reveal the solution solving for n. So working all this out, simplifying, multiplying both sides of my inequality by n squared and dividing by 0.0001, and then square rooting both sides, we get n is going to be greater than or equal to 90.7. Now n is a number of partitions. It needs to be a whole number. So we're going to round that up and make sure that we have n large enough to meet this maximum. We want our error to be, at the most 0.0001. It's okay if it's less than, but it can't be more. So we want to bump that n up to 91. And remember that when you are estimating a definite integral with the trapezoidal rule, you can have sort of, any number of subintervals or partitions, if you will. So n being 91 is fine. Now, if we're using Simpson's rule, where the subintervals need to be grouped up in pairs, that would need to be an even number, and we'd say that n was 92, which is an issue that you're going to see in the last part of this example, where we calculate n for Simpson's rule as opposed to, of course, trapezoidal. So there is the work to our last example, finding the required n so that the Simpson's rule will get an estimation of the definite integral that is within that requirement of 0.0001 on the maximum error. And with n needing to be greater than or equal to 8.6 to meet those requirements, we have to take that up to an even number, which is greater than 8.6, of course. That is going to be 10 because of the requirements, again, of the Simpson's rule. You need to have those subintervals in pairs so that, we talked about in the previous lesson about getting the idea of those equations of those quadratics passing through the 3 points that you have when you have your subintervals lined up or adjacent to each other. So there is the end of our last example. Going through the arithmetic and simplifying and solving this inequality, we have that n must be greater than or equal to 8.6 for the Simpson's rule approximation to meet the requirements that the maximum possible error must be less than or equal to 0.0001. And because with Simpson's rule, we need to have those subintervals paired up, we need to have n be an even number, so we're not going to just round up to 9, we're going to go to 10, again because of that requirement, and that is the end of my last example. I'm Mr. True. Bam! Go do your homework.